So my name is Michel Rutten. I work for FHIR, the company that organizes this event. I've been programming for a long time. Here you see the Philips machine that I actually started on. That was before the whole Windows time, 8-bit. And gradually I specialized in healthcare. And in FHIR I specialize in profiling. I create Forge, that's the profiling tool for FHIR, a Windows.NET application. I'm going to show it in this presentation. So that's mainly my area of expertise. This is what we're going to discuss. Well, if we get up to it. Why do we need profiling at all? A little motivation. We're going to look at the conformance layer, the parts that FHIR provides, so you can do profiling. We can look at profiles themselves and extensions. How do you add elements to FHIR profiles? Time permitting, I'm going to talk a little bit about packages and new development in the FHIR specification. And finally, implementation guides and the registry, because you want to publish your profiles and share them with implementers. So let's get started. Why do we need profiling? Well, FHIR provides a platform specification, but you need to adapt it to a specific use case. And that's why you need a profile. It's a further adaptation to a context of use. So which resources do you use in your use case? I'm going to model a patient and observation, for example. Which API features? I only do read. I don't need write, for example, but I do need search. Which terminologies? You could do some value set bindings. In my use case, we use LOINC. And how to map these to the local requirements. And all of this is part of a profile. And what FHIR aims for is to author that in a structured manner. So you could write that down in a Word document, but that's just readable for a human. We want machines to be able to reason about it. So we want to author as much as we can in a structured way, in a machine-readable way, independent of any format. We now have XML and JSON, there might be more in the future, so it's an abstract format. I want to publish these profiles in a repository so people can find them and implement them. And because they're structured, we can use them to validate, to generate code, to generate a user interface, et cetera, et cetera. And again, this is only possible if we do it in a structured way, so it's crucial. So let's look at the basic components that FHIR provides. Terminology is not really part of profiling, but it's so key part that I included this in the little picture. There are many more resources in FHIR. If you go to the resources page, you get a large overview. You've got 120 resources. Most of them are medical or clinical resources, but there are some infrastructural resources. That's the resources that FHIR uses to build itself, because FHIR is built upon itself. And those are the resources we use for profiling. So we have some terminology resources, mainly value set, in which you define your terminology. Structure definition, that's the key. That's how we define the layout of a resource and the layout of an extension. Part of a structure definition is a list of element definitions. We can map these. And then we have, for example, the operation of the server. You can read a patient, you can write a condition, you can search on observations. With message definitions, you can define your searches, you can search patient by last name, for example. And again, this is all structured, computable. And finally, there's a resource to support creating implementation guides, and again, provide some machine-readable structured authoring to that, and testing, test script and test report. The core are these two, structure definition and element definition, and they walk into all the other ones. So the structure definition, FHIR uses that to define all the core data types. Coding, codables, concept, address, human name, that's all the data types. They're expressed by means of a structure definition. The resources themselves, patient, observation, condition, also structure definition is defined by means of a structure definition. There's some recursion there in the FHIR specification. Also the constraints, so these two, that's the FHIR specification. But this is what you create. Now you can create a US patient. So that's what Argonaut did. They took the standard patient, they constrained that to US specific constraints, and they did it by means of a structure definition. Again, and you can define a new element, or maybe it's a complex element. And again, you do that by means of a structure definition. And you can even define abstract models that are not related to FHIR in any way, and we call it a logical model. And again, we express it by means of a structure definition. So anything that has structure in FHIR is modeled by means of structure definition. No one is doing that. What can you do? You publish it to a repository, you can compare the two, and you can do a diff because it's expressed in a structured way. So you can write an algorithm to look at the changes, as Graham just discussed in his meeting. You can use it to transform between FHIR versions or to a different standard, maybe. You can use it to validate, very important. Does this patient resource that's on the wire, does it conform to the Argonaut profile? And you can compute that. And you can use it to generate code and user interface. And again, it's possible it's computable. So this is the recurring theme. Everything is computable. That's core. A little less important, but operation definition, it's simpler, but still, what's the name of the operation? We have a read, input-output parameters. I need a patient ID, for example. Behavior, if you send me ID, I'm going to give you back the patient resource that's associated with that ID. Clear cut. Works on which resources? Well, this is on patient. So very simple. And all the operations that a server supports are expressed by means of operation definition. So you can get a list, enumerate them, and reason about them. Again, computable. Search parameter. What's the name of the search parameter? Well, maybe search patient by name. Which resources? Works on a patient. What's the parameters? You send me some text and I'll match that on the last name field and I'll give you back a list of the patients that match. So you can extend, restrict the API. And again, computable. So you can get a list of all the search parameters that a server supports. So a client application could dynamically enable, disable buttons, for example, or screens, depending on the server and the capabilities that it advertises. And this is actually how that works. A server publishes a big resource called the capability statement, and that contains all the other ones we just discussed. So typically, if you have a client that works with a generic server, it'll get that capability statement, and it'll enumerate the list, which resources does the server support, which operations, oh, I can only read, I can't write, which server parameters do we support, etc. You can dynamically tweak your user interface to enable or disable certain features. Or maybe say this server is incompatible with my application. Again, computable. So that's within our serialization formats. Maybe a server just supports JSON that we didn't implement in XML. Security, I require, for example, Smart on FHIR, this is a secure server. Operations, server parameters, resources, I only deal with patients, for example. I don't accept all the other clinical resources. And which profiles? Maybe this server is constrained and I only accept Argonaut conforming patients. And again, you can all define that in your capability statement, and it's computable, it's structured. Finally, we get to the implementation guide, and that's a resource that's created to support the process of authoring an implementation guide. You don't need to use it. You can write an implementation guide just using a text editor and paste some images inside and then have a folder with the resources. But it's nice if you have something that groups it together. So you have the option of using this resource if it kind of fits your use case, and you can even share these implementation guides over the wire and reason about them. So it's to publish and to validate. And the implementation guide will contain narrative, but also a list of profiles and terminology, value sets, for example. So it's a two-part. Part of it is targeted for the machine, and part of it is targeted for humans, for implementers. Computable, again. And here you see there's a picture I took from the FHIR standard itself. And you can see kind of a broad relationship between these profiling resources. Implementation guide in the middle. This would be the part of the narrative where you just describe in text and pictures what you need to do, the use case. But you also reference all these structured resources that describe your whole use case. And again, for a capability statement that advertises the capabilities of a server, that also walks into all these resources and gives you a list of structure definitions and a list of operations, search parameters, etc. As I mentioned, the nice thing is that FHIR uses itself. So as of DSTU1, we try to define FHIR by means of FHIR. And that's how we, from DSTU1 to DSTU2 to STU3, these conformance resources, they got tweaked and they improved. Partly because we use them themselves to define FHIR, and sometimes we got stuck, so we had to go back to the resource and tweak that structure definition to make it work. So it's been tested quite a lot, and they're quite mature, these resources. So you can see FHIR is it's a bootstrap, like the Baron von Munchausen. It pulls itself from the swarm on its own boots. You know, and we eat our own dog food, so we discover these errors before the implementers run into them, which is Nasty. A little bit of canonical URL. In FHIR, all the resources have a unique identifier, but the conformance resources, they have a special way of identification. That's called a canonical URL. So you assign the canonical URL. That's something you make up. Usually you use your company domain that you control as part of the URL. And you might have multiple instances of the profile all over the world because you publish them to different registries, but they will all have the same canonical URL. If you look at the resource ID, that's server assigned. So if I post a profile to 5 different servers, they get 5 different resource ID. But I need to know that's the same profile. That's the same value set. That's the same code system. And that's why these conformance resources, we identify by means of a canonical URL. So this is how it would look. This is the canonical URL of the core patient. You can see here's the domain, control.hl7. Typically, it's followed by FHIR because you might have multiple standards on an endpoint. Then the data type, in this case structure definition, and then finally a unique identifier. Oh, in this case it's a patient. So if you would create a profile yourself for the fictitious Acme company, you would put your domain in front to make sure that you don't have any conflicts with other organizations, and use that same layout. FHIR, data type, and then a unique identifier. But if you post that profile to 3 servers, they will get different resource IDs, but they're all copies, they're clones of the same thing. So let's go into profiles. So profile, for me, it's a kind of fuzzy word. It's overloaded, but when I use it within the FHIR world, I mean constraining. We're constraining a core resource. We're constraining a core data type. We might even constraining another profile. We can build layers of that, or constraining an extension, for example. Maybe a trick question. What's the difference between a data type and a resource? Raise your hands. There must be somebody that knows. Please.
I'll take a guess. So a resource is made up of data types.
Yes, but a data type is also made up of data types. It's close.
Resource has an identifier.
Yeah. You can post a resource to a server, and the server will accept it and store it and give you back an ID. You can't post a data type to a server. You can't just post an address to a server. The server will reject it. So data types only exist within the context of a resource, and then a resource you can post to a server and get it back later. You can't do that with a data type. It's also part of something. In all other respects, they're exactly the same. It's a list of fields with data types, and they can nest and walk into other fields. Here's the overloaded. Sometimes, FHIR, there were previous standards. You have V2, V3. When you talk with people that have been working in healthcare industries for a long time, they might have a different notion of the word profile. So just be aware that the term profile is heavily overloaded. Sometimes people think about something like an implementation guide. They will call it a profile, coming from the V2 world. I specifically use the term profile for constraints on a resource. So I have a little narrower definition. But be aware, when talking to people and you see the term profile, kind of try to pinpoint what you're talking about. Is it a profile in a single data type or that broad notion of a profile? But I will call this an implementation guide to be specific, and that's what I call a profile. And that's usually how it's discussed in FHIR. I mean, even a conformance package. So that's a set of resources and value sets and operations that belong together. I already mentioned you can layer profiles. So if you look at the top, FHIR defines the core profiles, the core patient. And then, for example, Argonaut constrains them to the US level and puts some extra extensions on them and it strikes some elements. They've got the national profiles. And you could constrain them further. You could say, well, within Massachusetts, we have specific constraints we need to add to that layer. And you can define a regional level layer of profiles and then walk to into an organization or maybe even to divisions and further constrain them. So you can keep constraining and keep publishing layer profiles. And as you keep adding constraints, the number of resources that will conform gets smaller. So in my notion, you could view a profile as something, as a where clause in a query, and the bigger the where clause gets, the less records you get returned from the server, and eventually you can add so many returns that no resources fit at all. So, and the profile becomes very big, but your matches are small. It's kind of inverted. So what's in the structure definition? Well, first of all, there are some basic metadata. Canonical URL, very important. You have to assign that and make sure it's unique. A name and a title. There's a status, so you can keep it in draft, so it's clear when you publish it to a server. People know this is still being worked on until it's final. There's a date and a version, an author-assigned version. There's also something as a FHIR server that updates these versions, but that's an automatic process on the back end. All resources have that. But the conformance resources also have an author-assigned version, where you can assign a version that you use within your organization, for example. And you can make sure people know who to contact when they see an error in the profile. You can add publisher. And you can refer to the base profile. I'm constraining the Argonaut patient, so you point up. And of course, then there's a list of element definitions. So if you go to the spec, this is how that's rendered. The name of the elements, each element has a data type. There might be some description added. There might be default or fixed values, usually not in the core spec, but you might add that in a profile. Complex constraints, saying if that field is empty, you have to specify that field, for example, with an expression or a length limit. Terminology bindings, very important. So that's how you fix a field. Say you have to use a loin code, you have to use a snowman code. And mappings to other specifications. And out of the box, all these resources already have a bunch of mappings on them created by the working group. So you know how to map to V2, V3. But if you extend and you create your own profile and define new elements, you could add your own mappings. About these complex constraints, in DSU1, we try to do that using XPath. So say, well, if this field is empty, you have to fill that in, or stuff like that, these complex constraints that walk into different fields. It was kind of hard because it's stuck to XML, and FHIR supports multiple formats. FHIR also supports JSON and now protobuf, and maybe in a couple of years we'll have a new format. So XPath doesn't fit to that. And it's hard to express. Stuff like slicing in FHIR, those XPath expressions got really, really large, and it's kind of write once. Lloyd could write them, but then nobody could read them again, and you have to do it again. So it wasn't a good fit on FHIR. It was a long discussion, but eventually we decided to define our own query language, FHIR path. And that's independent of a serialization format. Here's some examples. Give me all patient names where the given name is Wouter, and check if it exists. So it's more of a fluent way of expressing these expressions. It's much more readable than the XPath. If you would do this in XPath, it would be much longer because it doesn't have these specific keywords. And this is not tightly bound to XML or JSON. It's just a query on the concept, on the abstract notion of that data. And it's used outside of FHIR. You can see it's also being embraced by Simi Group, QDM, so it's quite powerful. So how do you refer to a profile? Well, this is an example of a resource. We made an observation, I measured the cholesterol level of a patient, and I created this example resource of an observation. Now, I want to convey the message that this is not just any observation, it's a special cholesterol observation, and I'm conforming to a profile. So you can put a tag on this resource saying, I conform to a specific cholesterol profile. And you can see this is the canonical URL. So you can look that up in a server, find the profile with that canonical URL. That's how you make the match. And the profile contains the list of all the elements, and then you can validate, that resource, because this is just a claim. You can claim to conform to a profile, but a server has to do the validation to actually verify that claim. And you could also resolve these profiles locally on your disk, on your server, but you could reach out to an external server. So you could accept a resource that claims conformance to an unknown profile, and you could walk out and go to the HL7 registry and see if you can find that profile and do the validation. A little about versioning. Versioning in FHIR says if you add a breaking change to a profile, you have to publish it with a new canonical URL. That's the gist of it. You're allowed to do correct typos, for example, and change the comments. But if you really change the meaning of the profile, you shouldn't publish that as a final version with the same canonical URL, because it will hurt implementers. It will break the existing implementations. So the guidance is, if you have non-breaking changes, you can maintain the canonical URL and just bump that version, saying, oh, we added some clarification to the description, but if you do introduce a breaking change, publish it with a new canonical URL. So it's kind of an eternal contract. Once you put it out there, you have to assume that people start building systems against your profile, and you're not supposed to tamper with it anymore. When you open a structure definition, you might see something like a differential and a snapshot. When we exchange these profiles, we only exchange the constraints that that specific profile adds. We don't exchange the whole data structure because it's kind of bloated and it's not necessary. So when the server receives that differential, it knows how to calculate all these implied constraints. And that allows us to keep the volume of these structure definitions small. Again, if you want to work with them, a computer needs to know how does that whole patient with all the extra stuff look, and then you need to calculate that snapshot. That's a hard process, but there are server operations that support that, so you don't need to do that yourself. But just be aware, if you open a structure def, you might find the same element definition twice if you do a full text search, because maybe the profile contains both, and then you get a sparse list of elements, and you find the patient name, but also in the snapshot, so they might be twice. So take care when you're scrolling through the thing if you're looking at the right component. This is only if you're working with the XML and the JSON on a low level. If you're working with tools, you will never going to see this. This is just for the implementers. So how do you author profiles? Well, in DSG1, of course, we didn't have any tooling because we're still building the standard. So we had to do it by hand. We had to manually write the XML and the JSON. Or there was an Excel tool, and the HL7 community kind of made a script that you could save that Excel sheet, and that converted it into a structure definition. But it's not an ideal fit. Excel is a grid. It's not a tree. So it was hard, and I wouldn't suggest to try this, maybe once. So fortunately, there are tools. Lantana company made a Trifolia that actually it's existed before FHIR. It supports multiple versions, v2, v3, and FHIR. It's an online tool, so you can go to this URL and sign up and create your profiles. There's a UML-based tool made by Dave Carlson. You can find it at this. They've been working on this for a long time. That's before FHIR. That supports v2, v3, also FHIR. And that's based on the UML modeling. So you create a UML model, and the tool converts that to a FHIR structure definition. And then finally, there's Forge. That's a tool that I create. And that's specifically made for FHIR. So Forge doesn't know anything about v2 and v3. It only understands structure definitions. And that's what it does. So, and it's a graphical user interface. So let's go into extensions. Well, sometimes you need some extra fields. So you need to add a field, for example, to the patient. And a very famous example is race and ethnicity. It's mandatory to administer this information in the United States. It's strictly forbidden to administer it in Europe. So we can't put that in the standard. So for fields like this, we create extensions. So with Argonaut, they can put these extensions on the US patient, but in Europe, they're not part of the patient profile. So this is a clear example of why we need it. And usually you look at if 80% of the systems in use support a certain field, then we put it in the standard. And if it's part of the 20%, then we say, well, that's more of a candidate for an extension. That's the famous 80-20 rule. So how do you find it? Well, it's just a structure definition, just like it's like a data type. You need to assign a unique canonical URL. Well, this is my extension. Where can this extension be used? Well, for example, race and ethnicity, they're useful on a patient and a person, but not so much on a condition, so you can express that. But you could reuse it in many profiles. So once you publish an extension to a registry, many people might use that extension and refer to that in their own profiles, especially race and ethnicity. That's been referred by many different patient profiles in there. So how do you use it? Well, in FHIR, all the elements allow you to add an extension. Each element has something like an extension collection. And out of the box, it's empty, saying, well, you can add any number of extensions. I don't have any rules for it. So just send them to me, and I'll store them, but I don't understand them. And a profile, then you can add constraints to that collection, saying if you send me a patient, you have to add the race and ethnicity extensions to the root. And those are mandatory. You can add other extensions. I'm fine with that. I'm just going to store and come back to you. But those two I actually need. If you don't send them to me, I'm going to reject your patient, for example. And that's what you can express in the profile. And again, you refer to that by means of the canonical URL. So for example, here we have a patient record from Irma, from HL7 in the Netherlands. And she has nationality on it. So this is an extension. So this example resource conforms to the Dutch patient profile that we created with some additional rules for our country. And in that profile, there's a nationality element added, and that refers to an extension, the patient nationality extension, and that's actually a separate profile. So again, by means of the canonical URL, first you can see, it conforms to NL core patient, and an NL core patient will refer you to that extension definition, and that's how you can see how it's defined. And then we find out that it's actually a code with a certain period. So the basic examples are primitive extensions. A primitive value, like maybe just a string value or an integer, your body weight or something. You see a lot of those extensions. Most of the extensions that you can see in the registry is just a string, an integer, or a Boolean. Like a birth time, for example, or a birthplace, which we would string. Oh, this is complex. But sometimes you need something extra. As we see at the nationality extension in the example, that had two fields. There was a code and a period, because you live in a country for a certain period and you move. So we need a complex extension. And it's just the same actually in FHIR. You can add sub-elements to the extension and create your own data type, like human name, like address. A little about packages. We've been using the implementation guide resource before we had this, and this is kind of a new discussion that's recently started, maybe in January or a little bit before in Cologne. And we noticed that the implementation guide contains the narrative, but also that all these structured resources. And for many use cases, we just need that latter part. The computer just needs these profiles and the value sets. I'm not interested in all the HTML and the pictures, so there's no use in sending them around. And then, we looked at, as developers, we looked at how we deal with that in our own IDEs, and as developers, we have something called a package manager. I can pull in binaries from published by other developers and use them in my own software, and then the tool will help me to install that and to say, oh, there's a new version, and you can update it, and it will warn me when it's no longer compatible. And it kind of made sense to try to do the same within FHIR. A profile is not a code, but the needs are the same. We need to publish these, someone else needs to install that, and needs to refer to that, and maybe in a while needs to update it. So we introduced the notion of a package manager in FHIR, and now Graham is already publishing these packages for the core standard, and we're now creating tools. And hopefully when you start creating a profile, instead of finding the Argonaut profiles and downloading them by hand from their website, the tool will just build you like a little search box, and you search for Argonaut, and it'll find that package, and you push install, and it'll download it, and it'll pack it to a folder, and then you can start using these Argonaut profiles or extensions, for example. So we look at NPM, that's a famous package manager from the Node.js. It's quite popular, and it's no use reinventing the standard, so we just try to reuse this technology. There will be some additional features, like you need to resolve a canonical URL, but basically, it's NPM technology. And you can see, for example, in my colleagues have been working in Holland to define some profiles, and they're actually layered. So the MedMy profiles, they're based on some medication profiles in Holland. They're based on the core HL7 profiles in Holland, and they're based on the STU3 FHIR standard. Right now, if I need to do that, I need to find all these different profiles from different spots and put them on my hard drive, and I can start working. And it's a tedious process. So the package manager, you will just point to this, and it'll figure out the dependencies and get the whole thing for you. It saves a lot of time. You can see it follows the hops. A little bit of implementation guides. There is a resource in FHIR called Implementation Guide Resource. You don't need to use it. Sometimes people get stuck and try to change their whole workflow looking at the resource. You don't have to use this resource. You're perfectly fine creating an implementation guide in an online wiki editor or in a Word But you can use this because it adds some extra structured support. As I mentioned, the first part is the narrative. That's a list of pages, a list of Markdown or HTML pages with some formatting. You can add some images, maybe some, you want to add a PDF or an Excel sheet, something, you can add some attachments. And the second part, that's actually the structured part. And that's a list of profiles, operations, searches, etc. And what we're now doing is kind of splitting this off and basing that on a package. So one can see from STU3, there is no package. This is still part of the implementation guide resource, but I expect in the coming months it will be moving very fast through this whole package manager infrastructure. And then the implementation guide resource can do what it was designed for, create implementation guides. And all the other different structured use cases, they'll be covered by the new packages. So you can see an implementation guide might define the package, but also add the narrative to it. Well, how do you create them? You could create them manually, an implementation guide resource. Again, you could write the XML or the JSON by hand, but that's kind of tedious. So usually you generate this. There's a tool that allows you to create some pages and some narrative, and then finally you say publish, and it outputs this list of HTML and a FHIR resource called an implementation guide resource. And the resource, the nice thing is because it's kind of a manifest and it mentions all the files, it allows you to exchange that between servers and they can walk into the resources and find them in the profiles. So you can publish it through the registry and you can use it to render the content because it describes the layer of the pages and the structure. This is the intro page, and then you have the tree structure of the document. And that's what the resource actually adds. So if you read, you have the list of pages, you have the resource, and you can build up a website and render it. And that's actually how the FHIR standard itself is being published. So again, the dog fooding. Oh, we mentioned this. So you could even convert it to a PDF or something if you have like a powerful system behind it. Because the structure is in there, the content is in there, the resources are in there, and those are all the ingredients you need to display it. Yes, let's move on. So how do you author them? The FHIR community itself publishes something called the IG Builder. That's a Java tool, it's command line. It's just open source, you can download it, it's being worked on all the time. And you, by means of configuration files, you run it and it will build the IG for you. It's very powerful, it's more catered at developers and people that are familiar working with the command line. So the FHIR specification itself is created this way, and also, for example, dev organout IG. My company, we created Simplifier, an online FHIR registry. We took a different approach, saying, well, I think not all people are comfortable working with the command line. Some people prefer like a point and click, a visual environment, so create more of an online editor, and it's a different approach. Of course, you can't script that thing, but it's much more easy to find out how it works. And then you just go to the online editor, add some pages, add some resource, and that renders the thing for you. And for example, the devices working group from HL7 used it to create an implementation guide or an HL7 Germany. The output is the same, it's just the way of working is different. And again, if you output that implementation guide resource, you could eventually move these implementation guides from one system to the next and have interoperability on the IG level. So a little notion I want to give you from, I do have some background in CMS, and that's where I learned about this. There's a workflow while you're creating the draft phase, and then finally when you publish it, you kind of throw it over the fence, and then it goes online, and people start building it, but it's not, usually you're not finished. Usually you will start working on the next version, and eventually that published version will get a version 2, and a version 3, and then eventually you're going to mark the first version as obsolete, and then eventually maybe retract it. So there's also a workflow on the publishing side. I think that's, so when you start authoring profiles, it's useful to already start thinking about how we're going to deal with in 5 years if we're going to publish version 2 of the standard. Because, you know, the registry. Well, if you keep these profiles to yourselves, then everybody starts creating patient profiles and we have no interoperability. So crucial for profiling is that we publish these and that we encourage the whole community to first search for prior art before you create your own profile. And for that, we need something like the Google FHIR, where you go and you input your search query, And it'll tell you if there is something existing that you can use. For example, the ethnicity extension. So the FHIR organization actually controls this, the FHIR registry, and that's where you can find all officially published profiles. What is official, the author determines that. But it'll be no longer in draft, it will be final. And there's also an implementation guide registry where you can find all the official implementation guides published within the HL7 community. For example, Argonaut. And that's also up there on the FHIR.org URL. So you're strongly encouraged when you start profiling to first look in these two registries before you start creating something new. There's also Simplifier.net. That's actually the back end of the HL7 registry. Something created by my company. That's not just official profiles, but you can find all kinds of profiles here. It's open for everybody, so you can put test profiles in here and draft profiles. But there will be official profiles on here. For example, lots of HL7 affiliates, working groups are working on Simplifier, the local affiliates. And there might be even private profiles on there. So what can you do on the platform? The HL7 registry, that's a fairly simple web app. It's just a search box. You put in a search query, it gives you the profiles, you can download them. That's about it. But of course, because it's structured, you can do a lot more, and Simplifier tries to leverage the power of the profile. So you can use it to validate your examples, send it to the registry and say, well, here's an observation. It claims to conform to the LDL cholesterol profile, but can you verify that for me? And then the tool will run the validation and give you the result of that. Also, you can see incoming and outgoing references. If we all put our profiles in the same global registry, then now we can see who's using my extension. If you publish your own extension and other people start using that, you want to know, but you don't know how. Well, in the registry, you can see which profiles are referring to your work. That's very useful. And you can get some statistics. And actually, as I mentioned, Simplifier is the backend for the HL7 registry because HL7 is not a software company, so it's being fed from here. And it also allows you to create implementation guides. This is the online editor I just mentioned, where here you have the tree structure. Here you can add some narrative. You can see the special instructions saying, render me a profile or render me the XML, so you don't have to do it by hand. Again, because it's structured, so let the computer do it for you. Finally, I want to end with the Profile Academy. There's a lot to tell about profiles. I could keep talking all day, but it's just, I think, almost finished. So we did put up a lot of information that we kind of discovered while we're building profiles, and you're all encouraged to go here and start learning about profiling. I did prepare some exercises, so after this tutorial, I will be upstairs on the profiling track, barring some meetings I will attend, but most of the time I will be there, and we work on exercises. I created some synthetic exercises, but again, that's just a made-up example, and I would really prefer to work on actual hands-on use cases. So if you have profiles, extensions, bindings you're working on, please bring them to that table, and we'll try to work on that. And if nobody brings something, then we'll just pick up a synthetic exercise. I will do it step by step. So if you never work with a profile, we'll take you through the whole process. Start very simple constraint, build it up from there, and time permitting, walk all the way to building an implementation guide and publishing it to the registry. So you're welcome to join me for the track. And I think now we all need some coffee. Do we have time for questions? Are there any questions? Well, one, please. Yes. No, there's no automation involved. You have to do it by hand. And you have to look, because for each resource there might be breaking changes in the core spec, but it kind of depends on the resource that you're profiling. Observation might be stable, but a different, device component might have huge breaking changes, so you'd have to redesign your whole profile stack. So that kind of depends on the use case. And there's no tooling for that, no. Thank you.